So our next conic section is the hyperbola, section 11.3. And a hyperbola and an ellipse have some similarities and then a very, very big difference. So notice we have that formal definition again of what a hyperbola is. You've got a set of points in the plane, that is the hyperbola. The difference between two fixed points called the foci, so instead of the addition of them, the difference between them is what creates all the points on the hyperbola. So you can see there's a lot of information here. Our focus will be on a couple things. I want you to focus on the equation of a hyperbola. That's, obviously a really key thing here. So you should see the x squared over a squared, but minus y over b squared equaling 1. But because of the fact that you could have the difference, one of the x squareds or y squareds could be negative. So you could also have, in the second case here, the x squared could be negative instead of the y squared, and that does create a different hyperbola in terms of kind of the way it opens up. There's going to be vertices for the hyperbola, but it only has one set due to the fact, not surprisingly, that since one of the x squareds or y squareds is negative, if you were to try to find another set of vertices, you'd end up with the square root of a negative, and we can't have that. So there is only one set of vertices depending on the type. And you could have this thing called the transverse axis. It's not a focus for us, but we do talk a bit about the asymptotes. So the asymptotes are these lines right here, and they're very helpful because they lead us to which way our hyperbola goes. Asymptotes, we know it's going to get closer and closer to these asymptotes, so it gives us the shape of the hyperbola. So we'll care about those. We don't focus too much on the foci for the hyperbola, but we, just like with the ellipse, you want to be able to recognize, hey, this is the equation of a hyperbola, just like this is the equation of ellipse or the equation of a circle or the equation of a parabola. You want to be able to recognize those things. That's definitely key. So just taking a look at the first one here, and we'll take a look at an example. If you think about, this is the first example here, coming down here, I want you to notice that because the x squared over a squared is positive, that means that we have x-intercepts, which are our vertices. So that's happening right here and right here. These hyperbolas that we're going to be talking about now do have, it matters that the fact that we have, we can think about 0, 0 just in terms of the way that this is shaped. What you should see is the asymptotes go through that 0, 0. So the asymptotes are just lines. They're just lines. And the slope of those lines come from the values, as we've seen many times, underneath our x squareds and y squareds. So it's just the ratio of those. You can see that that's actually b, which is under the y squared, and a, which is under the x squared. The ratio of that creates the slope of the asymptote, plus or minus. And once we know the asymptotes, as you can see, you can kind of see here, once we know what the asymptotes are, and once we know what the vertices are, we really have a good idea of what our hyperbola is going to look like. So it's just another conic section, what happens when you take a slice of a cone. You can see that if you have your x squared being positive, you're going to open to the left and to the right in this hyperbola. And if you have the y squared being positive, you're going to open up and down in the hyperbola. So do notice those two things. And let's take a look at an example. So we have y squared over 16 minus x squared over 9 equaling 1. So this is the standard form of a hyperbola, as you can imagine from seeing it in the big text box. So we have this equation. Taking a look, you should notice that we have the x squared being negative. So this is our second situation here. So we do want to pay attention to that. And so the idea here is, because you see that the x squared is negative, it's going to have vertices, but only for the y. So what we do to find them really is just recognize that, again, I'm going to flip back and forth here, but you can see that we have a squared under the y. So that's telling us that a squared equals 16. And so for us, that means that a equals 4. And really, that's going to give us two vertices, not surprisingly. It's going to give us the 0, 4, and it's going to give us 0, negative 4. And so that is two values on the y-axis. Go ahead and graph those, just put those dots on here and here. So already you know that the hyperbola is going to come up like this, the hyperbola is going to go down like this. That's in contrast to the ellipse, which is instead of going up, it comes down, instead of going down, it comes up. That creates the ellipse. So that subtraction sign is really the key thing that tells you that you have a hyperbola and not an ellipse. So we have our vertices because a is 4, just by definition of what a is. And then notice that b is 3, and that's simply because we know that b squared is 9, so that tells us that b is 3. And then that allows us to find the asymptotes. So asymptotes. So let me come back over here one more time. So our asymptotes are going to be created in this case, as you can see, by two lines plus or minus a over b times x. Plus or minus a over b times x. So let me just write that out. So notice that will give us, we just do a is 4 over b is 3 times x, and also the negative of that as well. So 4x. Okay, so remember the whole idea behind the asymptotes is that it allows us to have our hyperbola see what it's approaching and getting close to, and that gives us the shape. So all this is, notice the intercept, y-intercept is 0, 0. All we need to do is start at 0, 0, and then do the slope of 4 over 3. So positive 4, positive 3, and then a negative 4, negative 3 will give me the first asymptote, just using that slope of 4/3. So let me draw that asymptote here. Okay, and then we do the same thing with the negative 4/3. So we'll go up 4, but to the left 3, and we will go down 4 and to the right 3, and then that will send our other asymptote this way. There we go. And then all we do is start at the vertice there. And, well, it'll be easier for me just because of my tablet here. To start on the side, I'm close to the asymptote, and then I come down to the vertice, and then I go back up to my other asymptote. So here's half the hyperbola right here. There you go. And then we do the same thing down here at the bottom. This one might be a little easier for me to do half and half, but I just want to get close to those asymptotes. And you know, it should look similar, should be symmetrical and stuff, but that is what the hyperbola looks like in this case. So again, focus on your vertices, get those vertices, whichever vertices you have, get the asymptotes, draw those, and then just do your shape. And notice there are no x-intercepts on this. So notice it never crosses the x-axis. And if you want, you can just take this piece of information, but you can see very easily if there were x-intercepts, then when I let y equal 0, which would create this equation, I would end up with this, which would give me x squared equaling negative 9 if I tried to solve for x. But you can see x squared can't equal negative 9. There's no value that you can square and get a negative. So that is not possible, at least a real number, I should say. And so it tells us there's no x-intercepts, which, you know, we knew anyway. I've already said it. but you can see why that is, that it's pretty easy to see. And so again, the big difference between the ellipse and the hyperbola. So no x-intercepts. Okay. All right, so we have another example. So the first step on this one would be to write it in that form where it's equal to 1. So if you want, you can take a minute, you can pause, and then you can see if you can write this in that form that you see on the text box on the first page. Okay. First thing I'm going to do, I'm going to take that constant over. Then I'm going to divide both sides by 100. We have x squared over 25 minus, oops, gotta get my squared in there, y squared over 4 equaling 1. So now it's in that form that we recognize, hopefully. And we see that since one of the terms, x squared or y squared, is negative, in this case the y squared, that we have a hyperbola. So we recognize pretty quickly that when we think about the vertices, because the x squared is the positive of the squareds, that we are going to have x-intercepts in this case. So I have x squared over 5 squared. If you want me to just do another line here, y squared over 2 squared, just writing it in that form, which allows me to say that a is going to be 5, and that gives me 5, 0, as well as negative 5, 0. So these are my vertices, also x-intercepts, which means we will have no y-intercepts. Just a reminder, no y-intercepts. You should not be crossing the y-axis. Besides the vertices, really all we need other than that are the asymptotes. Now we can come back if we want, since this is the other case, this is the first case that we were looking at. We have a situation like this. We can see that in this case that our asymptotes are y equals plus or minus b over a, plus or minus b over a. So we'll come back here, here, plus or minus b over a. And so what that's going to give us is y equals b2 over 5, and y equals negative 2 over 5. And again, that's times x. Gotta have that. Put my x here as well, of course. And now we're going to graph those lines that have a slope of positive and negative 2/5. Whoop. And then we'll be able to draw our parabola. Okay, so get those asymptotes going. So I'm going to start at 0, 0, since they both have that intercept, up 2 over 5, and down 2 to the left 5. So that's one set of asymptotes. And then I have, so what you should see from that first page is that we're creating like a little box. You should notice that. So it might be pretty easy to see that we're going to have this point here, and then this point here, which is still just the slope of negative 2/5, but it does create this little idea of a box that gives us everything we need. And now we're going to start again at our vertices and just going up to one asymptote, down to the other asymptote. This is opening to the right, and then up to this asymptote and down to this asymptote here. And then here's another graph of a hyperbola. So in thinking about the guide to conic sections, this is a good way, this is a good reference here to just think about. This is like if you have a general equation. So for example, this is just general. So notice it has, each piece has a squared piece, and then you also have, each of them have a linear piece, and then you have a constant as well. So depending on what the coefficients are of those terms and what the constant is, that will help you to figure out what situation you have. So there's a few different situations here. If A or C equals 0, so notice it's or. If A was 0, you'd have a y squared but no x squared. If C were 0, you would have an x squared but no y squared. So by only having one x squared or one y squared, that should tell you that you have a parabola. Now, if A and C are the same number, so the same number in front of A and C, whether that is 1, whether that is 5, whatever, as long as they are the same, you will have a circle, because you can always write it in that form, x squared plus y squared equals some number. Okay? So A and C, if they are the same thing, you are good. Okay? Now there are situations, I'll mention something which is not common, where you can see that you might have that situation, but you actually have a point or nothing, and that's dependent on the f, that's dependent on the constant. But typically, most of the time, very often, that's going to be a circle. Now, if A does not equal C, but they have the same signs, so they're both positive or they're both negative, they're not the same number, but both positive, both negative, that's going to give you an ellipse, because you're going to be able to add them together, and even if they were both negative, you could divide by that negative. Again, f matters, but that's kind of the first thing to think about if you see A and C being different numbers but having the same signs. And if they are opposite signs, then one's positive, one's negative, vice versa, then you're going to have a hyperbola. So one of the most important things to take from all of the conic section work is just being able to look at an equation and say, what is this thing? Whether or not you can graph it like that or do other work with it, can you just recognize what the shape would look like? Which of these four things is it? That's key. That's the first step. That's the first place to get to with the conic sections. And that's section 11.3.